everything that we have been able to do is due to these three men, and others included Newton, Boltzmann, and Feynman. And what I'm going to do is first give a little retrospective on the history of molecular dynamics, at least as far as I'm concerned, the more important aspects of it, and then show some applications we've made of it over the years. So the first, I think, molecular dynamics simulation that I'm aware of was done in 1955 by Enrico Fermi, and this is a paper by Pasta, Ulam, and Fermi at Los Alamos. Now, at that time, Fermi was a professor at the University of Chicago, and but he would visit Los Alamos for the summers and on weekends sometimes. And he was always very, very interested in the question of ergodicity. The issue being, since all of statistical mechanics is based on assumption of ergodicity, that the systems of interest are ergodic, he was, and there were no real theorems aside from Birkhoff's theorem, which wasn't very useful. He decided to simulate a chain of particles in one dimension. He had 64 particles that could only move along this one dimension, and he fixed the end ones, and then he assumed that the interaction was harmonic between nearest neighbors, and he put in some anharmonicity as well. Now, if it was harmonic, the problem is you're definitely not ergodic, because you could resolve the system into normal modes, and if you put energy in one mode, it would stay there forever, so it would never equipartition. Statistical mechanics tells you, of course, that these systems would equipartition. So the only thing that would make them equipartition is the nonlinearity. And so he put in a nonlinearity, which is the second term here, this term over here, and he took n, the power here, to be 3 and 4. So I should have had 3 and 4 over there, not 2 and 3. Actually, it's 2 and 3 because this is the force. So the potential would be have third and fourth power, but the force has 2 and 3. Then he excited a long wavelength mode. So you take the harmonic part, resolve it into normal modes, put a bit of energy into one of the modes, and then, of course, because of the nonlinear interaction, the energy should spread out, diffuse through the modes, and you should go to equipartition. That's what they tried. He wanted to see if it would, just in this simple model, do that. And he was interested in how long it would take too. But by accident one day, he ran the system long after the steady state was reached. In other words, he saw the energy distribute equipartitionally in some way. And actually, the way the story goes, they went out to lunch while the maniac computer that they had been programmed in it went out to lunch and came back, and lo and behold, the energy went back into that mode that he had excited initially. This was completely mind-boggling. And he didn't understand why, and never understood really why. He died, I think, 2 years later, or a year later. So he never understood it. But this simulation, I think, is the first molecular dynamics simulation that I'm aware of. And it's sort of a hallmark of problems that came later, in that the potential energy was differentiable. After he did this, a couple of years later, Alder and Wainwright looked at molecular dynamics of hard spheres and did a great deal of work on that. But that was discontinuous and not very relevant. Well, it's relevant in the sense of learning how to pack particles at high density to make a liquid, but it was not very useful from the point of view of current practice. Okay? Now, Metropolis followed this up, wrote an article in 1992 in Daedalus. Metropolis is the same Metropolis of Monte Carlo fame. Metropolis, these are quotes from his paper. First of all, of course, Fermi was a great physicist. He was one of the people who did both experiments and theoretical physics at a very high level. He was responsible, of course, for fission, not for fission, but he was the first to have a self-sustaining nuclear reaction at the University of Chicago. Actually started at Columbia, but then people thought this was too dangerous. So the story goes, too dangerous to proceed in New York, because New York was too important a city, so let's move it to Chicago. and so what he did, what Metropolis said, Metropolis was the head of the computer center at Los Alamos. And in fact, the reason Metropolis's name is on Monte Carlo in such a prominent way, according to people who were at Los Alamos at the time, is because he was the director of the computer center and gave them time. That was it, okay? It was really Ullum, von Neumann, and then Wood and so forth that did the rest. There's a plasma physicist who was the Metropolis Rosenbluth, and he did really the major work on Monte Carlo. Anyway, so what Metropolis said is Fermi and Teller were the first hackers. They actually loved the computer. They learned machine language, and they would, whenever the computer was available for other purposes, they would program the maniac. And so this was the first problem that Fermi really looked at in this. He believed that the above computer simulated discovery was to be his highest contribution to science. This is what Metropolis says. It is certainly the first major scientific discovery made by simulation, by computer simulation, at least as far as I know. Of course, there's an awful lot of work that was done on fission, neutron diffusion, that's in the classified literature. So Feynman, in fact, came to realize that reliable machines in perfect working order were far more useful than much that passed for theoretical physics. Now, I like to show this slide usually because when I was a graduate student, using computers in chemistry was considered beneath the dignity of a theorist, okay? And in fact, that went on for many, many years. And I asked, where are those theorists now? Because this is sort of taken over. But back then it was this. But it was very interesting to see Feynman and physicists were actually very, very keen on using computers to solve scientific problems. According to George Gamow, the maniac computer stood for Metropolis and von Neumann and stole awful computer. Yeah, that was also in this Daedalus article, which is very interesting. Okay, then after that, I'm ignoring Alder's work completely, even though there were some very major things that he did. But the paper that really got the whole ball game started was a paper by Anis Rahman, who was at Argonne National Laboratory, and he looked at spherical particles that interacted according to a Lennard-Jones 12-6 potential, and he put them in a periodic box and solved the equations of motion, Newton's equations of motion or Hamilton's equations of motion, numerically, and was able to determine the paired correlation function, which tells you the structure of the liquid, and to get velocity correlation functions, which just tell you how velocity at time t is correlated with a velocity at a time before it, for a single particle. So you could think of a particle starting out, moving, and then banging up against its neighbors. And so initially it's moving sort of freely, and then it gets collided and it gets back reflected, and there's a negative region in this which shows the backscattering of the particle against its cage walls. Well, that was a big surprise to all of us. I was a graduate student at that time, and I was working on time correlation functions. And most of the approximations you ever saw for time correlation functions in those days was that it was exponentially decaying in time. And this little negative region really was quite a surprise. But then when you thought about it, it wasn't such a surprise. Well, and so part of my thesis was to explain this. And what we did was in fact, it's one of the first actual attempts to use memory functions in time correlation function theory to compute time correlation functions. And lo and behold, I got this negative region, and I got a power spectrum. If you compare these two, in fact, the one with the dots on it are Rachmans, and so that was a big deal. Here's Anis back then, and so after I did this, Anis invited me out to Argonne, and the reason I had got to do this is that I think Stuart Rice, who was my advisor, came back from Argonne. He had given a talk there with a preprint of this paper, and he gave it to me, and I was just primed to do this work. You know, everything I read all these papers on correlation functions. Incidentally, in those days, you couldn't learn about them unless you read the papers. You couldn't get a textbook or anything. It was really quite unfun. And I was just primed, and I remember this idea I had in the shower, and I came in and I did it. It was done within a week or so. And so he invited me out, and I became very impressed with molecular dynamics. I said, this is the future. This is what I agreed with Fermi. This was important. After all, Fermi thought it was important because he realized that that was just the beginning of using computers to simulate nature. And so that's why he thought it was so important, not just because of the problem he worked on, but because of the methodology. So I came to Columbia, having done this, and I was teaching statistical mechanics, and I had a very good student in my class, came up to me. He had been working for a nuclear chemist in the department, Jack Miller. And at that time, Jack and I were very good friends. And Jack asked me, is there any way to simulate what would happen in a nucleus if you put a lot of energy in it, and how would the nucleons boil off? And there was this liquid drop model of that. So I had suggested using Boltzmann equation with Fermi statistics, and George was his student, so George Harp, and so he ran it on the computer. He solved the equation on the computer, and lo and behold, that was a very famous piece of work. And everywhere I went where there were nuclear chemists, they thought I was a nuclear chemist, and I'd be on their schedule. I'd go into the room, they start talking to me and asking me questions. I said, I don't know a bloody thing about it. But then George said he wanted to work for me, so he switched over. And he said, do you have any computer program for me, anything computational for me to do? And he said I was a systems programmer at Boeing. So I said, aha. And at the same time, Martin Karplus had just left with Columbia. Martin hired me and then left. I scared him away. Anyway, Martin, I acquired, the chairman came to me and said, could you use any computer time? They're looking, because now there's a big hole in Martin's time. And so they offered me the computer time. And I said, nah, I don't need the computer time. And then I went home and I decided, you know, this was a gift horse. I couldn't really ignore it. And so the two things happened at exactly the same time. And so I told George the next day, yeah, I have a problem for you. Rachman has done atomic systems, spheres. Why don't we do molecules? Okay? And that's when I think the first simulation on molecules was done. Okay, this paper appeared in '68. This is one of the several papers we worked on at that time, but most of the work we did was presented in a big review article. And that review article, I didn't publish a lot of the work in papers, but in that review article. And that came out in 1970. But these papers are ones, and here we're looking at how angular momentum decays. The molecule that could rotate. There's an initial momentum. How does the momentum decay? And in fact, that's related in some way to the rotational diffusion of molecules. So, and you know, basically, if you had a rigid molecule, the rotation in a liquid would look like a random walk almost on the surface of the sphere. So it was looking at things like that. Okay, so that's the start. Then, this is an interesting story. I think this is the most important single paper in molecular dynamics in some ways, at least for the first 30 or so years in the field, and that was the study done by Anis, again, Rahman, and Frank Stillinger at Bell Labs. Story behind that is Stillinger came up with a potential. It was called the Ben-Naim-Stillinger potential, and then later this developed into another model, the ST2 model of the water and things of that sort. But so he wanted to run simulation of liquid water. He said, look, if you had to pick one solvent in the world, that would be the most important. And so, in fact, he came to me because we had done molecules, and he said, could you do this? Can we work this together, collaborate? And I calculated that it would take something like 8 minutes per time step for 216 or something molecules. So I said no, because I was very, after carbon monoxide and nitrogen were really more important. But the biggest mistake in my career, that we didn't get involved with that. But that, I think, is the most important. So they got the hydrogen bonding structure, et cetera, for water. There's been huge amounts of work on this because the potential wasn't good, but we made some progress. People have made progress on water potentials. But I think that's the most important one. And that led to this paper by Roski and Karplus, I think it was in 1978, where they did a dipeptide in water. There had been work on dipeptides before that, but not in water, in implicit solvent or in vacuum. This is combining Rahman's work and Stillinger's work, but now putting the dipeptide in. They had to have a potential model for that. And so this is the way it goes. It goes from Lennard-Jones spherical particles to diatomic molecules to water to peptides, and then on to proteins and so forth. Now, there are lots of technical details that go into the doing of these problems, including force field development and so forth. I'm not going to cover that. But before I say anything about that, there's a story with this. Now, I don't know whether to repeat this story. I think John Straub knows the story because he worked for Karplus. And but the story is that Martin wanted to include water, and he went to Anis Rahman and said, how would you put a dipeptide into water? How would you do it? And he said, I think I know how to do it. So they had a collaboration. And Roski was a graduate student of Karplus's. So in those days, there was, well, there still is, this facility in Europe called CCAM, and they would have at that time workshops. And so Anis would go to those meetings, and so Karplus sent Roski to the meeting. Roski and Karplus coded up the whole thing, and that was the beginning of this work. But you'll notice there's no Rockmont on that. Now, I don't know what happened, okay? But according to Roski, he was very important in this book. So Anis, who was one of my favorite people, has really made a dent. Unfortunately, he died maybe 30 years ago, almost 30 years ago. But he was really an incredibly nice guy. And anyway, so I owe a lot to him from my graduate school. Now, I'm going to be talking only about fairly recent work. So I'm not going to cite everybody in the group. On some of the slides, there'll be names. But I thought I would show how beautiful, how handsome everybody is. I couldn't find a picture for young Chan, and I couldn't find one for Lan Hua. But in this picture, this is Jagannath Mondal, Willem Sterneman, I don't know who that is, Joe Marone, and Raz Nistor. I collaborated with Rich Friesner, my colleague. Wu Hongzhou was a former student of mine. Tom Arkland, who was really a student of Friesner. Lingle Wang, who's in the audience. All those people should raise their hands. Tom Arkland will be here tomorrow. Ronan Zangi, who is a professor in the Basque University. And most recently, Pratyush Tiwari. He's a professor in Maryland now. So in the rest of the talk, a lot of the work will be from their groups. And I don't want to show that. Now, one of the more recent things we did, say in the last, although it started in 1995, was the question of, and I had it before, the role of water in molecular recognition and hydrophobic assembly. And so the Anders Wahlqvist, who was right over there sitting next to John Stroud, raise your hand, Anders, back in 1995, did a simulation of two hydrophobic plates, you're looking edge on them, in water, and observed, if I could get it to go, let me see if I can do that. Not going? Press the button. Let me go back. Okay. Although we didn't make the movie then, when you see those two plates are free to move, and then suddenly the water is expelled, and it drives the two plates together. Now that is a very interesting phenomenon, because the water is really undergoing a phase transition. When these two plates get close enough together, it destabilizes the water in the region between the two plates. This is called what we call it de-wetting, but a lot of people call it capillary evaporation. And so what you see is, as these things come close together, there's a sudden evaporation of the water, and it's a collective phenomenon. It's not one molecule at a time going out, but it's a collective phenomenon. And then there's a tremendous driving force that collapses the two hydrophobic regions. Now, in order for that to happen, these particles have to be close enough. But it turns out, if you do a theory of this, that the larger you make the plates, the further apart this will start happening. Okay? And it is a gross phenomenon, independent, it seems, of all the molecular models for water. Here we were dealing with, when Anders did the calculation, we used what were called Gay-Berne oblate ellipsoids, but more recently, we've done it with something like graphene plates and looked at the same thing, okay? And that's the picture of that. So that was done in 1995, and that became the basis for a lot of work. The Lum-Chandler work the Lumweeks-Chandler work is really modeled on this, that they saw this and they went crazy about it and they did a theory. We had a very macroscopic type of theory, which could account for it. Now the problem that hadn't been seen before was very important, because in order for the water to be expelled, there's a very big energy barrier, or free energy barrier, to the expulsion of the water. So you have a stable state where the water hydrates the region, and then if you bring it close enough, you would have to wait on a computer forever in order to go over the barrier and see this de-wetting. However, if you made this small enough, it turned out we just lucked out, okay? And so we saw this. Now, here's something that occurred before. This is really Stillinger's work back in the early 70s, where he was talking about hydrophobicity. And he said if you take a small hydrophobic particle and you put it in water, it could fit in the hydrogen bond network. Now, suppose you made this bigger and bigger, this sphere. Eventually, it would distort the network and eventually break hydrogen bonds, so that there has to be a difference between large-scale and small-scale hydrophobicity. Now, back in the late 1970s, we had done just this. We put a particle into water, and we also took two particles like this and put into water, and calculated the free energy as you bring them together. And we didn't see any extreme hydrophobicity. And the reason we didn't was because the particles we were using were too small. If you build up a cluster and make it big, then you start seeing this effect where you're breaking hydrogen bonds. And that's what, in some sense, is related here, only here the effect is entropy driven. Here, because you're breaking hydrogen bonds, it's enthalpy driven. And so this is basically an enthalpy driven transition, and we're beginning to understand this thing. Now, this became very important, as you'll see a little later. At the time we were doing it, it was purely theoretical. It was, in fact, I think Anders didn't know why we were doing it, and it was just my whim. I was very curious about what would happen. So, but we started taking it more seriously. Joe Marone, raise your hand. Okay, Joe. Worked on what happens when you took two buckyballs and put them in water, and also saw the same kind of thing, but in fact went on and did some very interesting work with this, if I could get it to go. It's the first time I'm using Keynote. So it's not as though you could just click on the thing, but you'll see that he has two spheres. Again, you have water. They're separated far enough initially to have water, and then eventually what will happen if you wait long enough. So we're just looking at the space filling model of water there, but you see this again, this de-wetting and this approach. Here's another example with a hydrocarbon case, and I don't know if I could do that, but I don't have to do it because I think you saw it already. So okay. Here's another case, Joan Shea, and we took looked at an Alzheimer amyloid beta AB protein, a protofilament, and we put water in between. We pulled them apart, put water in between, and then looked at what happened, and the same thing happens there. You see this driving. And here is a very important result. Ruhong Zhao and I, and this is longest. So this was a Nature paper back in 2005, and this was a tetramer of melanin, okay, for molecules, and they actually cluster. And if you look at them, and this is, you'll see there's water in there to begin with, and then you let that go, and again, you see this de-wetting. Let's see if we can get that to go. No. Oh. Well, anyway, let's not kill ourselves over that. But what you'll see in this case, oh, there we go. Okay. So as it collapses, as it's coming together, it again expels the water rather dramatically. And this was the first, I remember there was a big controversy about whether this de-wetting phenomena would happen in proteins. Part of the reason is the protein backbone is charges, is polar, and attracts water. It's not very hydrophobic. And of course there are hydrophobic regions, but maybe the charged regions would pull the water in. And so this is the first case we looked at where we saw a de-wetting phenomena in a protein system. There was a lot of argument. Most people didn't believe you would see this. And so that was part of the reason we did this simulation. Okay. Then, let's see, where were we? Okay. Okay. This is an example of Joe's work where we took actually this is something that was first done, at least a model like this was first done by McGammon, Andy McGammon, and he made a cavity, so he had something like that, and we had a buckyball going into it. And we wanted to do something large enough so we would have this dramatic de-wetting phenomena. He did it with methane going into a small hole, and there, of course, you don't see, or there's just a hint of it. So we wanted to see how de-wetting would come. And not only that, we wanted to get a theory for the reaction rate for binding. This was like a protein cavity, and this was like a ligand. And so we started getting interested in the question, what is the dynamics of ligand-protein binding, which I'll come back to in a little while. But we saw, in this case, that there was a dramatic de-wetting phenomena. And if you watch that fall, what you find is that the particle separated by water has to wait. It gets close enough, it has to wait for this drying transition, and then it goes right in. And so the time scale is really defined by the drying transition. And so you're waiting for this fluctuation to take place. And so what we thought about was the following. Suppose you were going back and doing diffusion-controlled reactions in which you had a ligand diffusing up to a site and binding to it. Would that be reasonable? Most people who do these kinds of calculations assume a simple diffusion equation, and McGammon has done a lot of work on that. But here, what we observe is that the water fluctuations in the pocket go from high to low, but look at the time scale, 4,000 picoseconds. That's a huge time. Usually when you do Brownian motion theory or diffusion theory, you assume that the solvent moves very rapidly compared to the degrees of freedom you're interested in. Whereas here, the fluctuations are slow. So Joe and I became very interested in trying to understand how to do a theory in which you had these two time scales. I'm not going to go into that. It's a little too more theoretical, and I don't want to do it. But it's a very interesting question. When you have very slow fluctuations, how do you handle reaction kinetics? Okay. So that brings me to more recent times, 2012, when David Shaw was, I don't know if you all know about David Shaw, but you probably do, a billionaire who's decided to spend his extra cash on a research center And we have somebody here, a guy by the name of Hua Fang, okay, former student. And these guys built a computer, Anton, where they can go, the usual typical time scales that we were able to go to as late as 2006, 2007 were microsecond. But these guys could actually go to milliseconds and maybe longer. So they were able to really start looking at interesting phenomena that happen on long time scales. And what they looked at was the mechanism of voltage gating in potassium ion channels. And I'm not going to go into great detail about this, but what they found was a de-wetting transition, that the switch between active and passive for the conduction of potassium ions through the channel was a de-wetting transition. So we were always looking for some interesting biological thing that needed this, and then we came across this. Actually, I spent, I think, 2011 at Shor's group, so I learned about it, and I said, hey, incredible. We have an actual application of this thing. Well, now there are more and more of these kinds of things where you see these de-wetting transitions. So in their case, let's see if I can get this one to work. Okay. These are the ions. It's a long one, so. Now, I'm not sure this is capillary evaporation. That's something we haven't established. You really have to look at the cooperativity of that transition. But eventually it de-wets. And when it de-wets, the ions can't go through. They have to be in an aqueous environment to go through, right? So this is an interesting thing. Okay, so, well, that's another example of it, but I'm going to go there. Okay, so that's sort of one theme that we've been working on in the past decade. And then the second one is how osmolytes function. Okay, so there are two kinds of osmolytes that we were interested in. There's urea, okay, and that's NH2CO. And then there's TMAO, which is a trimethyl nitrile type molecule. And what is found and is well known is that if you add enough urea to your solution with a protein, it'll denature the protein. When you add TMAO, it stabilizes the folded structure. Most often that's what happened. And there have been a whole host of attempts to explain the action of these osmolytes on the equilibrium between folded and unfolded structures. The TMAO, is, I'm told, is very important in sea life. I presume, and this is just my own idea, but I'm not sure, but you know, when you go down to great depths, you get pressure denaturation of many proteins, and if TMAO is around, maybe it guards the protein from unfolding. But the point is that there's a lot of controversy about mechanisms. There are two kinds of mechanisms that are discussed. There's a direct mechanism where the osmolyte directly affects the protein, like binding to it, and thereby causing a thing. And there's an indirect mechanism where it's thought that the osmolyte simply changes the structure of water. So, for example, if you were looking at a folded protein, and you know that the folded protein likes to bury in some way some of the hydrophobic residues, that an oil is not soluble in water, so the protein will fold. If you add urea, the thought is you could change the structure of the water, making it less water-like, more lipid-like. And so the protein can open up. And that's called the indirect mechanism. So we were very curious. And so we started doing simulations on this. One of the first simulations we did was on a protein, hen lysozyme, and we put 7 molar urea in. We didn't do, back then we didn't do the experiment with TMAO yet. So it was mainly urea. This was done with Ruhang Zhao at IBM using the Blue Gene computer when it first was developed. You know, I think it was like 2005, 2006. So how do you do that? Well, this is an example of the system. I'm not going to go into too much detail about it. N-lysozyme and 8 molar urea aqueous solution. There's the protein. There's the waters, and the blues are the urea. And the question is, what happens? Okay? So what happens is, in the laboratory, is that the protein denatures in urea. And so that's what you would expect. But to do that in pure, and incidentally, if you make a mutation at this tryptophan residue 62, and you mutate it to glycine, the protein unfolds even in water. And in other words, a single point mutation causes the denaturation of the protein. But, so our thinking was, well, probably better to look at the mutant than the native protein, because it's going to happen faster, and all we can do is a microsecond. Okay? Now, of course, if we had Anton at that time, we wouldn't have hesitated, but we didn't. So what we looked at, this is an example of what happens in urea going to 1 microsecond, and you make the glycine mutation, and then you start it in its native structure, and then you watch it, and you see that this does indeed denature, and it denatures within the time scale that we wanted. So here's an example where we have the native structure and the mutant structure, and these are the nearest residues to the mutation. And what you see is, in the mutant structure, it does indeed unfold much more rapidly. And we analyzed this. We decided that the direct mechanism is the way it does. And what you can see in the next slide is, when you look at that region and you watch what's happening in that region. Incidentally, this work was also done with Dave Terumali, who was a previous postdoc of mine. And so what you see is that the water starts to infiltrate the region, but the urea then displaces it, and finally unwinds the thing. So that was an interesting thing, and we therefore started to think about really how this works in more detail, and we went to simpler systems to understand how this happens. I'm not going to do that. Oh, we had some idea about why the mechanism for that point mutation working, because what we have is the tryptophan is actually in the native structure between 2 arginines, and so it's a ring system that we thought was holding the 2 ions, the 2 charges, together. If we mutate that tryptophan to a glycine, that releases what's holding the arginines so close together, and they flip open. That was the idea for that. So we decided, okay, let's go back. I'm really a chemical physicist. My mind starts to get bogged down with big molecules. And I've had to learn about these proteins, which has been a struggle. Organic chemistry was not my strength. Incidentally, a story about that was when I was at Brooklyn College, where where I took all my chemistry courses, the chairman at that time, a guy by the name of Chironis, had this brilliant idea that he would select a few students and have them finish all the chemistry requirements in 2 years. So I had organic chemistry, I had 2 semesters in 1 semester. And therefore, whatever I passed it was a struggle. But whatever I learned, I forgot, because, you really need long-term contact with these things. So it's especially, I've been reading organic chemistry books ever since. So the point with this is, why aren't they both doing it? Okay, so this is a hydrophobic chain in just water. So it's hydrophobic, and if you okay, that's doing everything. So this is in water, this is in urea, in a solution of urea, and this one was in TMAO. Now you'll see with water, the chain likes to form a compact structure. It'll fluctuate up and down, but the water, it's hydrophobic, so it's driving it to now the beads on this chain are interacting with Lennard-Jones potentials, so that there is a slight attractive interaction between them, but they are not happy. Water is not happy around them, and so you get that. When you looked at the chain in urea, it spent most of its time in an open structure, and we tried to understand that. And then in TMAO, it forms a hairpin. So TMAO is forcing it to be compact again, not as compact and globular as this chain over here. And what we did is we did a whole theory based on this. If I could do it. Oh, well, this shows you the radius of gyration of the chain as a function of time. And in pure water, you see that it's most of its time around the structure, the collapsed structure, occasionally going into a hairpin type term, and spends quite a little time opened up. And so, and you'll get a certain ratio of compact versus unfolded from that. And it'll be an equilibrium ratio that you'll get. In TMAO, you'll notice even if you started out with the chain stretched out, it spends almost all of its time in this region, compact. And in urea, it spends almost all of its time stretched out. So we thought we had an interesting case to study in terms of theory. And so I'm not going to go through the theory, but there was a theory that was really originally done by Wyman, Tanford, and Timoshev, which actually looked at how conformations of large molecules change as a function of things that can bind to them, of the concentration of things that can bind to them. And using that theory, there is a thing called preferential binding. This is the equilibrium constant for folded, from unfolded to folded, from folded to unfolded. That's the equilibrium constant, the logarithm of it. The derivative of that, this is like the chemical potential, but this is the activity. So how the equilibrium constant varies depends on a preferential binding expression, which I'm not going to go into detail. But what it shows is that if delta gamma is greater than 0, you'll get denaturation, and if delta gamma is less than 0, you get protectant like TMAO. And we showed that happens in these simulations, and we were able to try to understand what it is about the interactions that do that. So that was sort of interesting. Okay. Now, how much longer do I have? This is another topic, so I could.
5 minutes?
5 minutes?
Well, we need 10 minutes to go up to Super, right?
Yeah, we'll just
Well, remember, you took up 20 minutes.
the issue
It's not me, it's the president.
Yes, the president's going to be somewhere.
You can continue at Subo. We have for like 4 hours.
The only thing is the president's going to be at Subo at 2:30. So
More recently, in collaboration with my colleague Richard Friedman, and with various members of Schrodinger, why don't you all raise your hands? There's Lingle. Lingle really did a lot of this work, and Krylov, and who else? Oh, and Ed Harder. Anyway, so there have been these anti-cancer drugs that really interact with the macromolecule, the biological macromolecule, by binding to it in a certain active site, let's say. And this is Gleevec, so Time Magazine back, when was it? I think it says here, 2001. This was a miracle drug, and so there was a big thing about it in Time Magazine. And then 13 years later, they retracted a little. Relapse in large number of patients, not all mutations are near the binding site. So these cancer cells, these proteins, cancer cells undergoing mutations, and eventually you can have a mutation that makes the drug ineffective. So we got very interested in this. I had been working with Rich for many years trying to develop new sampling techniques, because one of the big problems in understanding drug binding is sampling the configurations. If you don't do long enough runs or you're very inefficient sampling, you're not going to get good induced fit. You're not going to. There's a lot of things that don't work. So we were doing lots and lots of work on this, and so I'm going to talk a little about more recent stuff. I won't talk about that. So we developed these sampling techniques, and Lingle was one of the major developers of this. We had, before Lingle did his work, we had developed in our group a method called REST, which was replica exchange with solute tempering. And it was an idea where you heated up a certain region of the protein, let's say the region of interest, but you had to decide what that was. It's very flexible what you want to do. So suppose there's some induced fit. It would be very nice to have a hot spot which allowed that fit to happen quickly. But in this replica exchange method, we would also sample a bunch of different systems in parallel, and each one of these got hotter and hotter in this region. And then, as they were running, we would try to exchange their configurations and accept or reject them with a detailed balance acceptance probability. And so whatever was happening at high temperature, presumably, could filter down and allow you to get over barriers and so forth, like the barriers we heard about this morning, which are big. And in fact, Lingle has now done sugars where the puckering barriers are very large. Lingle, what are they? They're around 20 kilocalories per mole? Okay, so we could successfully do that. But anyway, then when Lingle came along and he said, oh, that's well and good, this replica exchange, this REST method, but what you want to do is get free energies. And so he combined this method with free energy perturbation theory. And the beauty of working with people like Schrodinger is you could go and apply it to libraries, huge libraries of molecules, and see how well it works. Something I never did. I could never handle libraries, but Schrodinger people do this all the time. So he developed this very clever scheme, which is called FEP REST, and it looks like it's been very successful. And so we did a lot of work on that, and I'm not going to talk about it. what I want to talk about is, again, dynamics, because the subject of this talk is dynamics. Getting back to David Shaw, he investigated a drug molecule called dasatinib, which is an anti-cancer drug, and this is a tyrosine kinase, and if I could, okay, so he looked at the binding, and what he found is that this drug would find its binding site, and it would find it again, but it would, when it unbound, it would diffuse on the surface. But once it got locked in order to get in, it had to expel some waters and relax around that, so that then it gets bound. And he was able to do 2.5 milliseconds in this simulation. I mean, the movie represents a 4 microsecond run. The binding occurs in 2.5 microseconds, so it's reasonably fast. You could look at binding, that's important. And they only did one or a couple of trajectories, but really to understand the biochemical problem, you're going to have to do an ensemble of trajectories. There's not enough to just do one. So we thought that we have to find something that we can do that doesn't require a computer like Anton. Because Anton, you have to be a billionaire to get a computer like Anton. Actually, you can get time on the machine in Pittsburgh. I think there's an Anton machine that you apply for time on. And you can do. But anyway, the time scales that occur here for drug binding are in the microsecond to millisecond regime. That is for binding. But for unbinding, it's very long. Now, the effective part of drug design, everybody thinks that calculating affinities, thermodynamic affinities, is the only thing. You want to optimize the binding so it'll bind and last there. But the real thing that matters as well is how long it stays bound. And nobody knows how to calculate the lifetimes of the bound state. That can be minutes, can be hours, can be days. So if you're doing a drug design, you not only want to get affinities, but you would like to get the residence times, the lifetimes. So, and actually there are papers that show that really you should design a drug around lifetimes as well. And so I had the most recent postdoc I had is Pratyush Tiwari, who is an extraordinary postdoc. As I said, he just went to Maryland. And he came to me a couple of years ago and talked to me about using metadynamics to calculate rate constants. And I said, nah, no way, okay? I didn't believe it. So then I saw his paper when he worked with Michele Paranello in Lugano, and he sent me a paper, and I said, my God, that's good. And then he asked the postdoc with me. So obviously, what did you think I would have him do? I had him look at ways to speed up the computation of unbinding rate constants, okay, or lifetimes. Now, in this calculation, there are this method. Suppose you have just a cartoon double well, and you want to use molecular dynamics. You have a solvent, and you have this reactive degree of freedom, and you have collisions between the interactions between the solvent and the reactive degree of freedom, and eventually you'll get enough energy maybe to go over. And John Straub and I did a lot of work on these simple systems. How long ago? 30 years? Okay.
At least.
And of course, in one dimension. When you have multiple dimensions, it's a real problem. Anyway, if the barrier is high enough, you're not going to see it happen with straightforward molecular dynamics. So let's see if we could get that to work. This is the illustration of how metadynamics works. And metadynamics, I think, was originally developed not by Parinello, but I think von Gunsteren and then also Voter did work on this. But Parinello has really pioneered its usefulness in these systems. I think the Voter thing was on surface motion, surface diffusion. But this is the trick. You'll see that pure molecular dynamics doesn't get you over there. But with metadynamics, as you visit a point, it's like you deposit a speck of sand. And at that point, it can never return there. It introduces a repulsion so that the thing. And so as you're looking here, you're filling this up with those points you can't visit. And eventually, you get to the top and can go over. And what Tawari did, the method he used, said, okay, I know how to do this. I know how to get from this fictitious enhanced sampling technique. What Parinello had shown is you can get free energies. You could get the free energy as a function of the reaction coordinate and get the barriers and so forth. But what Tawari showed is that you could also get a rate constant. And this is what he did. I'm not going to go through it, but it's, yeah, I have Grubmuller and Voter. And he showed that under certain circumstances, you could really get a decent rate constant from this. That is in overdamped systems. We did a lot of exploration of this on model systems. Interesting for those who are interested in it, but this, really you want to apply it to something interesting. So this is a question of rough energy landscapes. Now the problem you have when you're dealing with a condensed matter system is that there are many coordinates. How do you know which ones to do this metadynamics on? And usually you want to pick one of these coordinates they're called reaction coordinates or collective coordinates. You want to know what those collective coordinates are. And it's all intuition for most part. People just say, it's the number of contacts, native contacts, or it's whatever. It could be any number of things. And they don't really know it. So the first step in doing this is to say, do we have a method for optimizing the choice of a reactive coordinate? And if we have a one-dimensional reactive coordinate that's good, then we could go back and use this Tawari thing, okay? So we've been working a lot on that, and we came up with a method called SGOOP, S-G-O-O-P, which stands for Spectral Gap Optimization of Order Parameters. And the question is to find an order parameter that separates the timescales for all the fast motion from this slow crossing of the barrier. And so this method SCOOP, which it's too elaborate to go into in the minute or two I have left, but we have this paper in PNAS, and we have a number of other papers, which shows how this works. And it works by finding the eigenvalues of a diffusion equation and maximizing the gap. The 0th eigenvalue is when you reach equilibrium. The first excited one is the slowest motion in the system, and that's the rate constant. And if you can maximize the gap between these two, then the reaction coordinate is good. So it's like trying different reaction coordinates, maybe taking linear combinations of reaction coordinates with mixing coefficients, finding the values that optimize this gap, and that would be the best one. And that works like a charm. And we looked at the actual unbinding rates, and we're able to get really good, surprising lifetimes for the residence time. And I don't know if I have much time. I was going to go through all of this, and I'll just leave it at that. But here's a typical unbinding trajectory using this method. What you find is that we've looked at this dasatinib, and we looked at a hybrid. There's a new anti-cancer drug which takes the statinib and binds another molecule, makes a longer molecule that seems to be still effective against the mutations that cause the statinib not to work. We looked at it, we calculated the lifetimes. These are like the trajectories on the surface. Oh, okay, I'm gonna stop. I thought I'd give Mr. Friedman a little bit of credit. But I'm really excited about this group, and so I'll stop there. Okay? Do we have,
We're fine, we're fine.
President's waiting.
She's coming here.
Oh, she's coming here.
Right? Yeah.
Okay. Any questions?
Any questions? I guess we don't have to rush, yeah.
So first, the S group looks really, really cool. How much sampling do you need in order to determine that you have a spectrum? Because usually with these diffusion equation
Not
methods,
much. You need
a
short
lot.
times. Short times actually can do it.
How short is short?
Took about maybe an hour, 2-hour runs, but we do many of them. But if you, obviously it depends on the system. So when I looked at the simple models, like the DeLeon-Berne potential, I don't know if there's where's Topper? DeLeon, he's a student of DeLeon, and DeLeon and I worked on a problem years and years ago. And so we tested a lot of this out on that model. Let's see if I have any. Oh, that was one interesting. See, the resonance time on this is 20 seconds. That's a measured resonance time as well. But I don't remember how long the spectral gap, but it's so much faster than doing full molecular dynamics. Yeah.
So Bruce, maybe I'll.
Hey!
Maybe I'll ask.
This is Dave Rumlow. He's the famous chairman of the chemistry department at the University of Texas.
One part of it's true, but not the famous.
If you want a job, you gotta take it.
Maybe I'll use this occasion to ask you to speculate on what do you think of the prospects of using computer simulations to truly discover a principle in biology or anything else that you think it can be done, and something that's can't otherwise be done.
That can't otherwise be done. That's an interesting question. Reminds me of a question somebody asked me when I first interviewed for my job at Columbia. If you had infinite commuter time, let's say you could get the result and turn it on, got the result, what would you first study? Okay? It's like that kind of question.
Yeah.
I didn't have an answer.
But some years later.
Some years later, I still have. The way I look at it, for computer simulation, I think the most important thing is justification of theoretical assumptions. To me, that is the most important thing. I never thought ab initio was going to be as important as it is today. So for most of my career, I looked at model systems, asked theoretical questions, tried to find approximations in the theory that could describe the experiment, the computer experiment. So that's the way I look at it. Now, if I look at it that way, in the history of computation, there are a few interesting things that happen. For example, Martin Karplus changed the paradigm early on. I remember when, and I always was amazed that most biochemists and chemists thought that the protein structure is rigid. And therefore, if you were to look at the in hemoglobin, the binding of oxygen or carbon monoxide to the hemoglobin molecule, that it was rigid and then the thing would have to get into wherever it binds. And he said, gee, that's not the way it goes in at all, because the barrier to that would be just enormous. you need to have fluctuations. That was a real eye-opener to biochemists at the time. Now you could say, it's not an eye-opener to you, right? But that's the kind of thing that maybe those little things are important. Okay? But I don't know. I think being able to design drugs is a pretty damn important thing. And as I get older, I think it's more and more.
And given that this is such a special event for us, Professor Anderson was kind enough to come and say a few words and present Bruce with a certificate. So thanks.
Great. I want to say hello to everyone. I'm very sorry I couldn't come to your talk, Professor. I had another obligation right at the time, but I have come over because it's so wonderful and important that you are here with us. I want to do a little reintroduction of him to kind of mark this moment, even though you probably know many of his accolades. And then I want to present him with a little memento of how we regard your extraordinary body of work in the world today and how much you've contributed to science. So I am thrilled to be here and thrilled to welcome you, Professor Bruce. And I want to make sure I'm saying your last name correctly. Is it Berne?
Berne.
Berne, to Brooklyn College.
It used to be said acid burn.
Acid Berne. The very hot acid Bruce Berne. We are thrilled to have you back at Brooklyn College. You may know that he's an alum of the college, graduated in 1961 and then went on to do his PhD work at the University of Chicago. We are thrilled to have him here. He has excelled in his field tremendously since that time. His important contributions to science are legendary, I think it is accurate to say, and they have earned him tremendous accolades. And while there are too many accomplishments to cite, I will simply mention a couple. He, as you know, is the Higgins Professor of Chemistry at Columbia University. He has published about 350 articles and 4 books. He is known worldwide as one of the pioneers of computer simulations of molecular systems, now which is an integral part of the way we teach chemistry. Recently, he was awarded the Peter Debye Award in Physical Chemistry from the American Chemical Society, an award that honors really excellence in scholarly work in this field. He has received the IBM Research Achievement Award twice, 2005 and 2007. He is a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences. And the list goes on and on. These are just the highlights, but it is fair to say that he is an outstanding alum of Brooklyn College. We are honored to have you here. We want to welcome you home. This will always be your home, and we want you to know that the entire Brooklyn College community is tremendously proud of you and grateful for your body of work over so many years. So I want to present you with a little memento of that, if I could.
Thank you. I should say a few words about Brooklyn College when I went to it.
Oh, I'd love to hear that.
So I paid $8 a semester.
Wow.
That was it. There were some other fees. If you happened to break a piece of equipment in the laboratory, they charged you. That's one of the reasons I became a theorist. But it was an extraordinary education that we got. And at the time I was here, my dearest friend Bob Silby, who died in 2011, was a co-student with me. Bob was an extraordinarily gifted scientist. He became Dean of Science at MIT and also won many, many awards. Another colleague of mine was Bob Morse, who was a professor of an organic chemist at Rutgers. Yes. My advisor, Stuart Rice, was a student here, and he went to the University of Chicago. And my colleague, Ken Eisenthal, also went to Brooklyn College. And Joel Leibowitz, for those of you who know about So it was an extraordinarily place. I mean, $8 a semester? My God. I almost learned organic chemistry.
What a cadre of excellence from this generation.
Yeah.
How much
Not only that, I've had my wife here. That's the most important.
It is, it is. Thank you so much, sir.